Exercise 2.2, we say that a context-free grammar is right linear if all the production rules are one of these three forms. We want to show that the class of languages that these can generate is precisely the same as right linear grammars. And the way we're going to do that is we're going to describe an algorithm that takes CFGs, where the production's in this form, and produces a NFA, and also that algorithm can be worked backwards. So these are the only three production rules we've got. And let's describe how we can make a NFA out of them. So the states of our NFA are going to be the non-terminals of the CFG, and the alphabet of the NFA are going to be the terminals of the CFG. So if non-terminal A can be replaced with X and then another non-terminal B, we're going to define our transition function to from state A, read to X, go to state B. If A is allowed to produce X, then we're going to define some new final state, we'll call it SF, such that from A, reading X takes you to this new final state. And once you're in the final state, you stay there forever. So delta of SF, no, because we read something else we want to reject. So that's fine the way it is. And if A can turn into epsilon, then that means it's sort of done producing strings. So we want A to be a final state if that's the case. Okay? We want to prove that the language that the grammar would generate is precisely the same as the language that the automaton represent. So that is, we want to prove if some string has a derivation from the starting state, that occurs if and only if from the starting state reading the string W is an element of the final states. Now, as it turns out, this is kind of too weak of a property. If you try to do the induction proof, it tends to fail. So what we actually have to show is that if there's some derivation for WT, where W is a string of terminal symbols, so terminals, call it terminal star, and T is a non-terminal, then this can occur if and only if from the starting state S, reading the string W takes you precisely to the state T. This is a stronger property than this, as we'll see, and we want to prove this property because if you try to prove the first one, it just doesn't work. The induction proof fails. So we're going to proceed by doing a proof by induction on string length. As usual, our base case is going to be when the string is empty. So if the string is empty, we want to prove that S has a derivation on the empty string if and only if the machine from the starting state reading epsilon goes into a final state. We want to prove this stronger property here. So we want to prove for any non-terminal symbol, S can produce epsilon T if and only if from the starting state reading epsilon takes you to T. Well, in this case, both sides are going to be false because there is no production rule up here that'll allow this to happen. We can't produce an epsilon here because X has to be a terminal symbol, so this side will always be false. And this side here, if you're an S and you read epsilon, you'll go to the starting state S, which is not going to be T because each of these productions is going to be a different state. Well, there is no production of the form, right? Because when we run this thing through our algorithm, the only way we're going to get a transition from S to itself is if this transition here is of the form S goes to XS. So this is not going to happen either. So for the base case, both sides are vacuously false, so it doesn't work. So now let's have a go at the step case. So we're going to, for the step case, assume the property is true for some string W. That is, for all non-terminal symbols, S can provide a derivation of WT if and only if from the starting state reading W takes you to the state T. And then we're going to prove the property for W with an extra character bolted on. That is, we want to show for all non-terminals T and for all terminals X, S can provide a derivation of WXT if and only if from the starting state reading WX takes you to the state T. Alright, so let's prove this, and we're going to start from the right hand side. So we can use the definition we can use the append theorem actually to break this up, right? Because you can read the W first. So this is true if and only if from the starting state, reading W takes you to wherever, and then reading the X afterwards still takes you into T. Okay, and then from the left-hand side, when can S provide a derivation of this string here? Well, the only derivations available to us are ones that add a character each time and another non-terminal, ones that make a character immediately, ones that return epsilons. The only way we could hope to generate this string here is if S could derive W and then some other non-terminal B, and then B can derive xt, because that's the only way to achieve this using only these transitions here. Okay? Well, if S provides a derivation of WB, well, we can use our inductive hypothesis, right? So this is going to give us B provides a derivation of xt, and delta hat of S reading W takes you into state T. So now we have these two facts here. Well, if I know this property is true, I can replace T, this is a B, right? S provides a derivation WB. Inductive hypothesis tells you from S, read W, go to state B. So we can replace the B over here. So this gets turned into a B, xt. Okay? If we have a derivation of the form B goes to xt, then by the definition of how I've constructed my transition function, that means delta from the state B reading X goes to T. So that basically confirms this property over here, and that proves the step case, which proves the property we wanted to show.